In this session, we are going to create a driving scenario using programmatically. In this example, you will learn how to generate the ground truth for a synthetic sensor data and tracking the algorithms by creating a driving scenario in a programmatical way. So you can also update this actor processes in open loop and closed loop simulations also. And plus you will see how to use the driving scenario to perform the coordinate conversion and also incorporate them into the bird's eye plot. So you can create interactively using the driving scenario designer app also. But here we will focus on the Matlab command line approach. So this will help you understand how to manipulate the driving scenarios for the various applications. And our main aim is to create, so just a minute, our main aim is to create driving scenario or a ground truth. So is to create a precise test scenario that is referred to the ground truth for testing out the sensors and tracking algorithms on a particular vehicle. So what is the use of this ground truth data in the sense? It is a very typically established in a global coordinate system. So since sensors are mounted on moving vehicles, we need to adjust the data to match the vehicle's movement accurately. So this driving scenario makes this adjustment seamlessly by allowing us to define the roads and object path in a global coordinate system. Additionally, it provides the tools to convert and visualize that information from the perspective of any ego vehicle within that scenario, that making it easier to understand and analyze. So finally, an example scenario is provided. Here we are going to create two vehicles. We are going to create two vehicles here and each positioned in a 10 meters apart. So moving towards the origin at a speed of the 3 and 4 meter per second respectively. So this example, how to define the vehicles within a driving scenario by using the Matlab command. So I am going to directly go to the code here. So first you have to derive the scenario. So what is a scenario? Scenario equal driving scenario. This line, it initializes a new driving scenario and assign to the variable, what is variable name, that is a scenario. So this driving scenario, it provides a framework for simulating our driving environments. Next, we have to specify our vehicle. So V1 equal vehicle of scenario of a class ID 1 and position 600 velocity also. So this line, it creates a new vehicle object within the specified scenario. So I'm going to break down this vehicle and V1 of vehicle inside this vehicle block. This scenario, it specifies a driving scenario in which the vehicle will be placed. And next one is the class ID. So what is the meaning of this? It specifies the class ID of the vehicle. That means it helps to identify the types of a vehicle, different types of vehicle. And next one is the position. So what is the mean of the position? This specifies the initial position of the vehicle in that scenario. So this position is specified as a x, y, z coordinate. In this case, the vehicle is positioned 6 meter along the x-axis and 0 meter along the y and z-axis. Next one is the velocity. So velocity of -3 and 0, 0, 0. So this specifies the initial velocity of the vehicle in that scenario, and this velocity we know already, we specified that one Vx and Vy, Vz components. In this case, the vehicle is moving at a velocity of -3 meter per second along the x-axis, and that indicating it's moving towards the origin. And next one is the yaw angle is a 180 degree. This specifies the initial yaw angle of the vehicle, which determines its orientation. So this yaw angle of a 180 degrees means the vehicle is initially facing in the opposite direction of the positive x-axis. That means facing towards the origin. So the same way we are going to create our vehicle 2. So V2. So we are going to initialize the new vehicle and assign to the new variable, that is what V2, and scenario in the sense it's a driving scenario which the vehicle will be placed, and class ID it helps to identify the different types of the vehicle. And here we mentioned the position. So this is the initial position of the vehicle in that scenario. That is belong to the x and y and z coordinates. So the vehicle is positioned in this case is a 10-meter origin along the x-axis. Sorry, along the y-axis, and 0 and z-axis will be 0. And next one is the velocity, and velocity is a 0 minus 4, a 0. In this case, the vehicle is moving at a velocity of minus 4 meter per second. Along the y-axis, that is indicating it's a moving downwards. And what is a yaw angle? Yaw angle is a minus 90 degree is a yaw angle. And now, I am going to run this one. So just a minute. Once you click this one, copy this here and paste it here. Now you are going to run this model. So first you have to, once you run this is your output. What is your output? Yeah. So this is your vehicle with properties. So first is the front overhang. This is how much of the vehicle it sticks out in front. And next one is the rear overhang. That is a rear overhang. It's a 1. This is how much of the vehicle it sticks out in the back. And next one is a wheelbase. So this wheelbase is the distance between the front and rear axles of the vehicle. And what is the entry time? So when the vehicle entered at the scenario, it's a starting time. That means we initialize the starting time as a 0. And what is the exit time? Exit time we should to the infinity initially. So when the vehicle leaves the scenario, that is set to the infinity initially. And next is the actor ID. So this actor ID is a unique number that is assigned to the vehicle in that scenario. And next one is the class ID, and class ID we already know this is the identifier for the type of the vehicle. And next one is the name. So the name of the vehicle if provided, if provided in the sense here you will get your name. And next one is the plot color. So the color is used to draw the vehicle. That is what plot color, and position and velocity and yaw. So yaw in the sense, just a minute, yaw in the sense the direction of the vehicle is facing initially. That means a rotation angle. And what is the pitch? That is a tilt angle of the vehicle front to back axis. And this is the height of the vehicle and also the RCS pattern also. That is a 2x2 double. So that pattern, that RCS pattern is used for the radar detection. That is why we mentioned that. Now we are going to visualize that scenario. So for visualize that scenario, we using the plot function. So now I am going to plot my scenario, and set to the limit also. Just copy this one and paste it here. So by using this plot function, just a minute. By using this plot command, it plots a scenario that has been defined. It visualizes roads and vehicles and any other objects within that scenario. And we are going to use a set function. So this sets the name of the plot window to the scenario plot. So this GCF this is the current figure window. That means plot window in our Matlab. And we specify the limit also. These commands, it sets a limit of x and y axis of the plot. In this case, x axis is the ranges from minus 22 and plus 20. Y axis also minus 22 plus 20. So this ensures the plot displays a specific area of that scenario. So adjusting these values, you can change the viewing area of the plot also. Now I am going to run this code. So this is our output. This is our output. We created a x limit and also the y limit. Minus 22 plus 20, minus 22 plus 20. And we successfully created a 2 vehicle in that plot. Now I am going to adding one more command here. What is the command? So AP equal actor possessor of scenario. So this line, it calls the actor possessors function on the scenario object. So this function, it collects the pose information. What is the pose information such as the position or a orientation, yaw angle or a velocity or an angular velocity of all the actors within that scenario, and organizes it into a structure format. So this resulting structure is then assigned to a new variable, that is what the AP. So this allowing us to access and work with the actor poses conveniently. So now I am going to add into my code. So let's see what will happen. Just close this output and see it here, see in the command window. So what is our structure format? So this output AP structure is a structured array that containing the information, the actor ID and position and velocity and roll and pitch and yaw angle and also the angular velocity. So each structure in the array that provides a detailed information about a specific actor within the scenario. So that making it easy to access and analyze the pose data of all the actors collectively. Now we are going to obtain the pose information of the all other objects. So I am going to use this code here. So minimize this one. Yeah. So we are going to specify the V2 target poses or a target poses of V2. So by using this target poses function, it gathers the information. It gathers the pose information of all the objects observed by the actor that represented by the V2. What is a V2? Vehicle 2. And transform that position into the actor's reference frame. So this means that the position of the objects will be relative to the actor's own position and also the orientation. So this assigns obtain the pose information to the variable. So V2 target poses for the further manipulation, for a further examination. This information can be useful for understanding the actor's perception. That means the vehicle's perception and also its environment. So now I am going to run this to the V2 target poses into our separate script. So once you click this, you will get your output in a command window. We'll just close this one. What is our output here? Yeah, so what is the actor ID? So this actor ID, it stores the unique identifier of the observed object. Next one is the class ID and it represents the class identifier of the observed object. Next one is the position. So what is the information? This position, it specifies the observed object relative to the actor V2. So it's always given as a x, y, z coordinate, and next one is a velocity. It denotes the velocity of the observed object relative to the actor V2. And next one is the roll. So this field, it stores the roll angle of the observed object that is relative to the actor V2. So it's representing its rotation around the longitudinal axis. So we know the pitch also and yaw angle and angular velocity. Now we are going to adding one more information to our plot. So that is a chase plot and we are going to create our chase plot and set the name of the plot. I'm going to give the name. So what this means by chase plot? So this command, it generates a chase plot from the perspective just behind the vehicle 2. So it provides a visual representation of the scenario that allowing us to observe the positions of the other vehicles relative to the vehicle 2. And this line, it sets the name of the chase plot window to the chase plot. So that is why we refer using the GCF. That means it refers to the current figure. That means a plot window in a Matlab. Now I'm going to run this one. Let's see what will happen. Yeah, so this is our chase plot and this is our scenario plot. So first we have to create our chase plot and this is our, what is it? First, we have to create our scenario plot. From that, we are going to define our chase plot. Now, we are going to adding one more element. So, I am going to go this one. So V1 dot yaw angle. So what is a V1 dot yaw 125? This line, it manually updates the yaw angle of the vehicle V1 to the 135 degree. This yaw angle, it determines the orientation of the vehicle. And we are going to update the plots by using the update plot function of the scenario. So this command update all the plots that are associated with the driving scenario to reflect any changes made to the scenario properties. And by using this, by calling this update plot scenario, you can visualize the effects of any manual changes made to the scenario properties. So that ensuring the plot accurately present the current state of the scenario. Now I am going to copy this one to my script. So just paste this one and run this model. Yeah. So this is the scenario plot, and we created the chase plot and scenario plot. So we tilt the angle. We'll tilt the 135 degree. Now we are going to convert the road boundaries into the actor's reference frame. So I am going to do that one. So for that, go to this scenario, driving scenario. So this line, it initializes a new driving scenario and assign to the variable name scenario. And as it provides a framework, as I said earlier. And we are using the road center. So this line, it defines the coordinates of the road center line points. So it indicates the definition continues on a next line. So that is why we mention the dot dot dot. So it indicates the definition continues on the next line. And this spot, this 0, 40, 49, and this spot, it specifies the x coordinate of the road center line points. And this is the y and y coordinates of the road center line, and this is the z coordinate. Next one, we mentioned the bank angle. So what is the mean of this? This line, it defines the bank angles of the road curves. And again, we specify the bank angles of the road curves, so that is a 0, 0, 999. This is the bank angles of the road curves. Next, we are using the road function, and inside this road function, we are using the scenario. We are going to call the 4 arguments. So what does that mean? It creates a road object within that scenario, and it takes the driving scenario, and it takes the road center line points and bank angles, and also the additional parameters, such as the number of lanes specified by the lane spec of 2. And finally, we are going to plot the scenario by using the plot function. Now I am going to add the another one more element, so that is the RB. So what is the mean of this RB? RB in the sense road boundaries. So this function, it calls or extract the road boundaries from the driving scenario. And it returns a cell array RB that containing the road borders, so which are represented as a solid black lines in the scenario plot. By using this road boundary function, we can obtain the geometric information of that road border. So which can be useful for the various purposes, such as the visualization purpose or analysis or a simulation. And next, we are going to create a new figure window. So this figure function, it creates a new window where we will make our plot. Next, we mention the outer boundary and inner boundary. So this line, it extracts the information about the road's outer and inner boundaries from the data we obtained earlier. Next, we mention the plot tree. So plot tree of inner boundary and inner boundary of 2 and inner boundary of 3. So this plot, the boundary of the road in a red, and each point on the road is represented as a x, y, z coordinate. And this plots the outer boundary of the road in a green color. So what does that mean? It's a green color and also the red color. So using the same method above. So this ensures that the scale of the plot is same in the all directions, that preventing the distortion. So in simple terms, this code, it draws the road boundaries in a 3D plot within a inner boundary in a red color and outer boundary in a green color. So this helps us to visualize the shape and layout of the road. So again we mention the ego chord. So again we mention the axis equal. So this ensures the scale of the plot is same in all the directions. So that's preventing the distortion. And again we use a road boundary function. So we mentioned the ego code. This code, it's demonstrate how to use the road boundary function or an actor to obtain the road boundaries in that actor's coordinate system. And next one is the ego code. So this line, it creates a new vehicle that is referred to as the ego vehicle within that scenario. So it specifies the vehicle's class ID and position and also the yaw angle. So yaw angle is a 30 degree. And finally, we are going to create a ego vehicle and placing it on the track. So we can use it to obtain the road boundaries from its perspective, which can be very useful for the tasks such as the navigation task or a collision advance. So now I'm going to create a new figure window, and by using this road boundaries function, we have to see our ego car. So this road boundary function is called with the ego vehicle. That means the ego car as an argument. So this function, it retrieves the road boundaries in the coordinate of the ego vehicle. And next one is the, outer boundary of RB1 and inner boundary of RB2. And these boundaries are extracted. These boundaries are extracted from the output of the road boundaries and assigned to the variables outer boundary and also the inner boundary. Next, we are going to plot the plot 3 of an inner boundary and inner boundary and inner boundary of 3. So this line, it plots the inner boundary of the road in a red using the plot 3 function. So it takes a 3 coordinates x and y, z for the inner boundary point. So the same way that is for the outer boundary. So that should be a green and red color. And finally we give the axis equal. And this command, it ensures that the scale of the plot is equal in all directions. That preventing the distortion. So now I am going to run this in our code. So V1 after the update plots. Yeah. Copy this code up to this. Paste it here. Now we are going to run this one. Just a minute. So why we do this? We create and we examine the road boundaries from the viewpoint of the ego vehicle in our simulation for the several reasons. So first, it allows to understand how the vehicle perceives the autonomous driving, and this is the figure 5, and this is the figure 5, and this one is the figure 4, and this is our boundary. So we successfully placed in our ego vehicle, and this is the chase plot view, and this is the scenario plot view. So which is finally it allows us to understand how these vehicles perceive the information, how the vehicle perceives its environment, which is very crucial for developing the autonomous driving system. So by visualizing these road boundaries as seen by the ego vehicle, we can effectively simulate the data it receives from its sensor, such as the camera or a lidar, a radar like that. So this simulated sensor data help us to test and refine the perception algorithms that ensuring the vehicle can accurately understand its surroundings. So visualizing the road boundaries from the perspective of the ego vehicle is a very critical step in the development of the autonomous driving technology. So by simulating how the vehicle perceives its environment and analyzing its different driving scenario. So this is the way you also you have to create your own algorithms also, and that helps to validate the simulation models and algorithms that ensuring that our autonomous driving systems.